Okay, so now we're on to Chapter 6. We're going to be skipping 6.4 just for your information. We'll come back to that later. That has to do with drag and resistive forces, and that's going to involve some calculus that we haven't learned yet. So we'll get back to this. So just a reminder about Newton's laws, what they are, and friction, right? Friction occurs because no surface is perfectly smooth. If surfaces were perfectly smooth, there would be no friction. But also there's electrical force between all the atoms, right? Really tiny, and so that slows things down. And there are different types of friction. There's static friction, kinetic friction. There's also rolling friction, which we'll study later on. Not very in depth, but some. And there's drag and resistive forces as well. Static friction is friction when an object is stationary, it's not moving. That's the friction that has to be overcome in order to start the thing sliding. And kinetic friction is what you have when something is sliding. Typically, kinetic friction is less than static friction. So once you push it and overcome the static friction, then the friction's a little bit less and relatively constant as the thing is sliding. This should all be review from last year. And so static friction equations, the maximum static friction, that's when you use μs, the coefficient of static friction. And but static friction can be less than the force, the maximum static friction. Kinetic friction you calculate as μk times Fn, and then rolling friction would be μr, rolling friction, but you're going to see very few, if any, problems involving that. Most friction problems, right? Every friction problem, draw the free body diagram, right? The free body diagram, drawing the diagram is really important. If you think it, write it. You've got to have some type of illustration or diagram, because once we start adding a lot of forces, you want to be able to see where do all of these things go, right? What are the forces that are balancing out or not balancing out? And think, are these forces more than the force of gravity? The applied forces, are they less than, or the force of friction, are they less than the force of friction? What direction is the acceleration? All those types of things. And so all you're doing really is applying Newton's laws. So in the first example here, you have a rope, and we're trying to accelerate a 30 Newton box. I'm going to draw this out so we can see all of the forces and everything. Okay, so here's the information that's given to us. The thing to do now is figure out, I don't think, actually the normal force is not given to us, but we can figure it out from this. If this is 30 newtons, this now I'm going to break up. So this is going to be 10 root 3, is that right? And this is going to be 10 newtons. So if this is 10 newtons, this is 30, that means the normal force here is 20 newtons. And so this also is like 17.3 or so newtons. The maximum static friction, Fs max, is going to be 10 newtons because it's, now I know the normal force, I can say μs, which is 0.5 times the normal force, right? So 0.5 times 20 gives me 10 newtons. And the kinetic friction force is 0.2 times the normal force, which is 20. And so that's going to be 4 newtons. So the first question is, will the box accelerate, yes or no? What we're asking here really is this force more than the force of static friction? The answer is yes. This is more than this. And so we're not going to have static friction. This thing is going to be accelerating. And since it's accelerates, so the answer A we already did. B, will it accelerate? Yes. And justify your answer. We'll say the x component of the applied force is greater than Fs max. And then part C says if the box accelerates, the time required for it to travel 10 meters from rest. Okay. So then I want to know the net force, so I can calculate the acceleration. Yeah. Hey, what's up? Come on in.
Are we doing the cars today?
Yep.
All right, because I tried it yesterday, but me and Mark had just totally failed.
You'll have like a half an hour to work on it in class?
Yeah, we have stuff. We just...
Okay.
Sorry.
Cool. No problem. You're good. fix that. Okay, so the net force then horizontally is 17.3 minus 10, or sorry, minus 4. Get that right? Yeah, okay, so it is 4. Because this is 17.3, this is 4. So this comes out to 13.3 newtons. And then I can divide that by the mass. This thing is 3 kilograms. It's 30 newtons, and so that means it's 3 kilograms. So the acceleration is 13.3 divided by 3, and that gives me 4.43 meters per second squared. Since I know the acceleration, now I can calculate the time it takes, assuming it starts from rest. It says from rest, right? So delta x equals VIT plus 1/2 AT squared. This is 0, because VI is 0. I know the acceleration. I know delta x is going to be 10 meters, and so I'm just solving for time. Let me go up here. So the time is the square root of 2 delta x over a. It's a bunch of algebra. Quickly. This is 2 times 10 divided by 4.43. Take the square root, and you end up with 2.12 seconds. All right, so now we want to find the tension in the rope attached to the 5 kilogram box. All right, so let's take a look at the 5 kilogram box. What are the forces acting on the box? You've got the force of gravity, you've got the normal force, you've got, so if this thing is sliding this way, that means it's exerting a friction force on it this way. So here's the friction force, Ff. That's going to be equal to this tension force, because the tension is going to be equal to whatever this is, because this is just staying in equilibrium. It's staying in the same place as being held there. And so I need to find this friction force. Well, this is mu times n, and mu, between all surfaces, as it says, is 0.2. So this is 0.2 times the normal force, which is equal to the force of gravity. And so that's going to be 50. So it's 10 newtons. Right, 0.2 is a fifth. 1/5 of 50 is 10 newtons. So that's the answer to part A. Now part B, the acceleration of the 10 kilogram block as it slides below the 5 kilogram box. Let's draw the free body diagram of this box. This has the force of gravity acting on it. It also has the force from this 5 kilogram box. So I'm going to write F5. Now the normal force is going to be these two things together. I've got 45 newtons from this applied force, and now I have this way, I actually have two separate friction forces. The friction force from the 5 kilogram box, so 5 friction, and then the force of the floor friction, or the ground friction. Okay, that's a lot of forces there. This is equal to 100. This is equal to 50. Okay, so this is just mg. This is the weight of this box, which was 50. The normal force then has to be 150 newtons. This friction force is equal to mu Fn for the 5 kilogram box, so that's the same as what this was. So this is 10 newtons. This is going to be the normal force on this box times the coefficient, so it's 0.2 times the normal force, 150. And so that 1/5 of that is going to be 30. So this is 30 newtons. This we know is 45. Okay. Notice I had to do all the vertical stuff in order to get this. So now the horizontal net forces are equal to mass times the acceleration. All of these are 45 minus 10 minus 30, because minus 10 minus 30 equals the mass, which is 10 times the acceleration. 45 minus, that's 40, so this is 5, equals 10 times A. So 0.5 meters per second squared is the acceleration. Okay, and now we want to know what is the acceleration of the box after it's passed out from underneath the other 5 kilogram box. So I'm going to do this over here, and there are actually a few things that change. All right, so I still have this 45 newtons. Doesn't say anything about that changing. I still have the force of friction from the ground, FGF. I still have the force of gravity, which is still 100 newtons. But now, notice I don't have this anymore. So the normal force now is only 100 newtons. That means the force of friction, I don't have this friction anymore. So this one is going to be 0.2 times 100. It's a different normal force now. So this is 20 newtons. So the net force equals ma. The net force, though, is 45 minus 20 newtons, minus this one, equals 10 times a. So this is 25 is 10a. So a is 2.5 meters per second squared. Okay. So we want to know at what angle will this thing start to slide. Okay. And we know that the coefficient of static friction is 0.5. Well, at the place where it starts to slide, that means that's the place where these two things are equal to each other. It's just at the point where this is going to break that. And so if I set these equal, Fg sine theta is equal to mu Fg cosine theta. When I'm solving for, let me get the thetas together, because really what I'm looking for is theta, right? How do I solve this? Well, if I can get sine and cosine together, sine over cosine is tangent. And so if I do this, Fg sine theta over Fg cosine theta is mu. Notice this cancels out, so I just end up with tangent of theta is mu s, right? And so then inverse tan of mu s is theta. So the inverse tangent of 0.5, I just plug that in as 0.5, gives me an angle of 26.6 degrees. And then part B, at what angle will the box slide down the incline at a constant velocity? Well, if it's in a constant velocity, that means these two are the same, except mu is just now mu k. So it's the exact same thing, except I'm just changing mu k, or mu s to mu k. So then for part B, inverse tangent of mu k, which is 0.2 theta. And so then if I plug in 0.2 for this, I get 11 degrees. Okay. Example 4 is similar to this, except it says that it's slightly inclined. And it's a 10 Newton box. We want to know, calculate the acceleration of the box that the plane is oriented at. 10 degrees, 20 degrees, 30 degrees. So it's kind of like what we had before with these angles, right? It's all the same situation, the same coefficients of friction. That means that still I have, if it's less than 26.6 degrees, it won't be sliding. So for A and B, not moving. We incline it to 10 degrees, it hasn't gotten past this yet. Incline it to 20 degrees, still hasn't gotten past this, so not moving. A and B, not moving. C is 30 degrees. Once it's at 30 degrees, now it has broken maximum static friction, and now I have kinetic friction here. And so I'm looking for the acceleration, so net force is ma. What are the net forces on it? Fg sine theta minus mu k Fg cosine theta, and that's equal to ma. Right. What we can do here also is get rid of the m's, because this is really mg, right? Mg, these cancel out, and so then I now have g sine of theta minus mu k g cosine theta equals a. It's just one less step that we need to worry about here. So this is going to be, we're at 30 degrees, right? So this ends up being, here I actually use 9.8. Right, 9.8 sine of 30 minus 0.2 times 9.8 times cosine of 30. You put that in your calculator, you get 3.2 meters per second squared. And that is it. That's the last example. The rest of these are kind of review. The next one talks about how the direction of the acceleration might not be obvious, so what you do is you guess, and then switch the direction if you get a negative answer, like what we did in the last packet. These on drag force, resistive force, and then centripetal force, these are previews. We're going to do some stuff on centripetal force as part of this unit. The drag and resistive force we're going to come back to later in another unit. Circular orbits, that we're going to get into quite a bit in our last unit in the mechanics section. So that's it for this lesson.